Hello and welcome to my presentation, Don't Touch Disk, Disk is Lava. Today we'll be looking at post-exploitation options for iOS web applications. So before we get started, we have the mandatory Who Am I slide. So my name is Marc and I have a background in pen testing. Now I performed pen testing for roughly 3 years before I moved into adversary simulation at CyberCX, where I did a lot of red teaming and purple team engagements. Earlier this year, I made the shift across to the boutique called Silent Grid, where I'm doing a similar role, mainly focused on red team engagements. So to kind of set the scene before we go through the content of the presentation, I'm going to walk through the following scenario. We're performing a red team engagement and we're targeting a particular client network. We've had a look at the perimeter, we've reviewed the services that are exposed and managed to identify a vulnerability that's affecting an iOS web application. So this could be some of the examples I've included on the slide, which I've seen in the wild in the last couple of years. Sadly, seeing a CVE from 2020 as early as last year, as well as found a bunch of remote code execution and LFI vulnerabilities in in-house developed applications. So if you're on a red team engagement, reviewing the external perimeter, as soon as you see something that looks a little bit dated and developed in-house, you're normally in for a pretty good time. No matter what, the vulnerability we found is going to allow us to upload a web shell to the iOS application, and then we're going to be able to start performing post-exploitation and push into the network. So as we go through the presentation today, we're going to look at 3 types of web shells. And as we step through them, we'll be increasing, I guess, in maturity in the approach. So we'll start with the basic web shells, which we've all probably used for capture the flags or even pen testing. So these are web shells that spawn a child process like cmd, and then just return the output to the operator from the standard output. Next, we'll have a look at reflective assembly loading, which is going to allow us to load our C# assemblies into memory within the iOS process, execute them in memory and get the output. Finally, we'll move on to how we can use deserialisation to achieve web shell-like functionality without the need to drop a file to disk. So let's get started with the basic web shell. So to demonstrate this, I turned to Google. I think most of my job's just Googling stuff. I had a look at this repository that I found by 10NC. Actually had the most hits on the Google page. So I had a number of examples of basic ASPX shells, which is exactly what I was after. But I also had a quick gander through there and found a number of web shells which looked like they'd been used in the wild. So that was pretty cool. Like they had some levels of obfuscation and looked a little bit custom. So if you're interested in that, check out that repository. Now the 3 examples I've included in the screenshots are kind of like snippets of the main functionality or how these web shells achieve execution. I also want you to pay attention to some of the strings that we're seeing in the example, like wscript.shell. We've also got create object, we've got exec, and then in the bottom examples, we got process, process start info, and we also got redirecting to standard output. So these are all commonalities between the 3 examples. Also note, if you have a quick look at the code, that they're all spawning a child process. And in the bottom example, you can't get any rougher than spawning cmd/c and then passing through whatever you want to execute. Obviously, they're capturing the standard output, which gets returned to the operator. So the first issue with this approach to a web shell is a very easy to signature stuff that's probably going to get caught by antivirus. Or in this example, I pulled a YARA rule from Florian Roth's GitHub. It's called gen_web shells. So, based on that, we can assume its intention is to detect various web shells. You'll notice that in this YARA rule, there's a number of strings that were in the first example. I probably should have tested it, but you just have to trust me, bro. This will very likely catch the web shells from the first example. Obviously, we can obfuscate this, and we're probably going to be able to deal with this type of dissection. What's a little bit harder to deal with, even if we can obfuscate the code, is dealing with behavioral-based detections, such as those by endpoint detection response, or even threat hunters like actively on the tools looking for suspicious activity. So I've included this excerpt from a CrowdStrike blog, and it talks about how their Falcon Overwatch team, which is their threat hunters, treat a hunting lead. And specifically, this references like IIS post-exploitation, and that's why I've included it. So it says a hunting lead might start with the creation of a user account, an event that happens routinely, but perhaps a web server is running on that host and a whoami command is run under the web server process. The occurrence of one or more potentially malicious hunting leads constitutes the likelihood that an adversary is operating around or outside of your security tools. So to further demonstrate this, I've just taken one of those basic web app shells. I've dropped it on my IIS server, but I've also run process monitor and filtered on the W3 WP process, which is the IIS worker process running the application. And as soon as we filter on process creation events, it's pretty easy to see that something not so great is happening. So I ran whoami and net user. So based on what CrowdStrike has said there, we're very likely to get caught by the Overwatch team if we're doing something like this. It's also something to keep in mind if you're testing a POC and you're worried about getting caught. You probably don't want to run POCs that are spawning like ping and any other system commands, because even just running the POC might get you caught. So at this point, we're pretty much swimming in the lava. We've got a pretty fat file on disk that's going to be easy to detect, and our OPSEC in our technique is not great. So before we press on, let's talk about what an ideal web shell might look like for us as an operator that wants to remain undetected. First of all, we want a minimal footprint for anything we drop to disk. This just goes across the board, doesn't apply just to web shells. The reason for that is it's going to be easier to obfuscate. We're not going to break anything or less likely to break anything. And it also makes it easier to embed in existing files on disk if we want to backdoor an existing file on the web server. Additionally, we want the code to be contained to the IIS worker process. So we want it all running in memory, and we don't want it spawning additional processes. And then finally, we want it to be modular. Again, we want a fully fleshed out web shell. We just don't want to expose that on disk. We want the ability to come load additional capability in as required. So this is where reflective assembly loading in web shells comes into play. Another CrowdStrike blog, a bit of a fanboy. This caught my eye because they're specifically talking about reflective.NET loading, so I'll just read it quickly. China Nexus adversaries are increasingly attempting access via stealthy implants and .NET execution through compromised Internet Information Services servers. In response, CrowdStrike Overwatch threat hunters worked with CrowdStrike's engineering teams to ensure this entry point has increased visibility. By honing hunting leads that focus on reflective.NET loading and IIS compromise, CrowdStrike Overwatch prevented China Nexus adversaries from achieving initial access. So must be doing something right. So reflective assembly loading is achieved with the .NET Frameworks assembly class. That class has a load method with a number of overloads. The most basic is you pass in a string with a path to your C# assembly on disk, and it'll load it into memory for you. But the method we're interested in is the one that accepts a byte array as the argument. So what it'll do is, as long as that's a valid assembly, or the bytes for a valid assembly, it'll load it into memory for us, and then we can use reflection to create classes, call methods, and use any other resources contained within it. So again, this is in memory, and it's not touching disk at any point. Naturally, this function, to some shape or form, is a staple of most modern C2 frameworks. So Cobalt Strike, have it implemented, Brute Ratel, Nighthawk, Havoc, and in the example I've included from 2019, a bit of a throwback to when I was doing some CTF labs and C# post-exploitation was all the hotness. We had Covenant. So Covenant, as a C2 agent, was like completely dependent on assembly.load. So when it called out to the C2 server, it would get pushed down a C# application, which would execute in memory, and that also achieve modularity. So if we were to implement this ourselves, we might have a function in our web shell that looks something like this. We're passing through some assembly bytes, which might have come from a file import, and then whatever arguments we want to pass to our C# application. So the first thing we do is we load our assembly into memory, but before we go ahead and execute it, we save a reference to the current console output, because we need to revert it later, and then we create a string writer, which we set the console output to, because that's going to capture the output from our C# assembly. Next, we call the entry point for the assembly. We pass through our arguments and it executes it. Once we've done that, we revert the console back to its original value, and then we return the output from the string writer to the operator, which is going to contain the output of executing that assembly. So if we were to re-implement one of those first shells, we'd have something like this. We've got a file input, which we're going to upload our assembly we want to execute with, and then we've just got a text box for arguments. And in the background, I've re-implemented who am I to simply print out the Windows identity of the process running the application. So when we upload that to our web shell, we're running as a default app pool account, which is a default IS application account. If you wanted a bit more of a fleshed out implementation, there's a tool online called Kraken. It was developed by seku_x11, and it's self-described as being a modular multi-language web shell. So it supports PHP, JSP, and also ASPX. And if you look at the ASPX web shell, under the hood, it's achieving its execution through that assembly.load. And again, just reiterating, it says Kraken follows the principle of avoiding command execution by re-implementing it through the functionalities of the programming language in use. And you can see in the little client application there, he's running PowerPick, which is a C# assembly, which implements the PowerShell engine, creates a run space, and allows you to run PowerShell within your process without actually spawning the PowerShell process itself. So he's doing that within the IS work process. Also going to show you my private implementation, Michelle, which I developed after leaving CCX. It's pretty much contained in a ASPX file. It's been minimized, but it's not quite the level of China Chopper, which is pretty impressive. It's 3 lines of code, if you want to call it that. That being said, when we compare it to the size of Kraken, we got 73 lines for Michelle and 429 lines of code for Kraken. And it's deliberately small, so you can't see my source code, but the source code with a white background is Michelle, and the source code with a black background is like some snippets of Kraken. So when you compare the two, pretty much the amount of variables set in Kraken is about the same size as Michelle, so pretty big difference there. I'm not dunking on Kraken, because Kraken's an awesome tool, and what he's done is pretty amazing. Just obviously a different design, and I'm sure if they wanted to, wanted their web shell to be more offset friendly, they could certainly achieve that. And Michelle's able to achieve its minimal footprint because the bulk of the functionality is loaded into or implemented in an assembly, which gets loaded into memory. So if we look at this logical diagram, it kind of walks through the server-side components of Michelle. We obviously have a client application, which makes the web server request for the operator. But we have that ASPX file, which we drop to disk. It has authentication, so you just pass through a string, it gets hashed and compared to a hard-coded value. Once we're authenticated, we can load and save our web shell assembly to a global key value pair within the IS application, and then any subsequent request where we want to make a command, it's going to retrieve that assembly by the global key and then execute the entry point method, and then that'll kind of hand over execution to our web shell assembly, which is in memory. So this is where a bulk of the web shell functionality is implemented. It's going to process a request, look at what we want to execute in terms of commands, and then grab any arguments and data it needs from the incoming request. So it's got things like upload, download files, as you would expect, and ETW and ANSI patching for defense evasion, and then that core capability of loading and executing assemblies in memory. So something like seatbelt or sharp dump or whatever your internal C# tooling is that you want to run. Because we've gone for modularity, it'd be super easy to implement additional capability. So object files are quite the hotness at the moment for a lot of the C2 frameworks, and there's public POC on GitHub for C#. So I could just rip the code, that's mine now, and then put it into the web shell assembly if I wanted that functionality. So we look at a demo now. I'm going to run you through how Michelle works. We have that config file. We obviously need to tell it where's make web request to. We've got some keys here. I don't trust operators to set fresh keys. So every time we generate a new file, it generates a fresh config with randomly generated keys. So it generated my ASPX file, my web shell DLL, and we can see fresh keys. So to simulate arbitrary file upload, You can do something very exciting and just copy a file to the web root. There we go, we've exploited the web server. All right, the first thing we need to do, that was easy. So what I'm doing here is I'm loading my web shell assembly into memory. So we can see the outgoing request in burp. A little bit fuzzy for you folks, but it's just base 64 anyway. If you can decode that in your head, that you deserve a clap. And then if we render it, we just got the default IIS page. So now we've loaded our web shell assembly into memory. We can execute the functionality discussed in the previous slide. But just for demo's sake, I'm going to run seatbelt. So seatbelt runs, we haven't passed an argument, so we get the help menu. From our perspective as the operator, it looks like it's running in the PowerShell window, but it's actually running in the context of the IIS application. So we can see that outgoing request now, where we've got our assembly. Let's try to render the page, but the output's in a hidden field. And there we can see the base 64 encoded and encrypted and compressed output, which the client application is presenting to us. So at this point, we're just touching Lava, files significantly smaller, reasonably OPSEC safe, but we can still do a little bit better and get rid of the requirement for a file. And we're going to achieve that by using deserialization. Before we talk about deserialization, you need to have a basic understanding of what the view state is. So view state for IIS applications is a capability that allows a page or a developer to store data client-side rather than storing it server-side and associating it with a session. So if you ever looked at the HTML for an IIS application, I'd be very surprised if you haven't seen a view state before. It just gets included as a hidden input and sent with every outgoing request to the page, and it's just that base 64 blob there in the screenshot. So with every request, the server's going to process that view state. It's going to update the values. It's going to do whatever logic it has, and then update the view state and then include it in the server response. What's actually happening under the hood is that base 64 encoded value is a serialized object, which has been serialized with the loss formatter. Funnily enough, there never used to be validation for view states. So the server would just trust any view state you sent up, would go ahead and deserialize it, which is obviously bad. So now they've implemented some kind of validation by default. So you either have message authentication code or message authentication code and encryption. And the keys for that are used to perform that validation are contained within the web.config or machine.config files. Sometimes it can just be in memory as well if it isn't explicitly set. What this means is if we can get local file inclusion, server-side template injection, or server-side include, we're going to be able to achieve a remote code execution primitive. Because we're going to get those machine keys, we then can create valid view state objects using the loss formatter. Luckily for me, I didn't have to really do any work. I just went up to GitHub, stole some code from ysoserial.net, which has 4 gadgets that you can use to stuff in a loss formatted object for the view state. The first 3 of those options are not super great because they all spawn in a process, which we're trying to get away from. But you'll see the gadget for the activity surrogate selector has some interesting functionality, which we've seen before, and that's the capability to load an assembly from a byte array. Additionally, when I was actually reading the help for ysoserial properly for once, rather than just skimming it, I noticed that Suresh, who used to work at cmd.exe, had included a POC for his Ghost web shell in the ysoserial.net project. So if you go through the directories there, you'll find that somehow flew under the radar. I'd never heard of it. What it does is when it's run in the context of an IIS application, it creates a virtual path provider, which effectively acts as a directory on disk, except it's completely memory resident. And then it has the capability to serve virtual files. Again, they're treated as a file as though they're on disk, but they just remain memory resident, which is pretty cool. So obviously for the Ghost web shell, we're going to hard code our web shell into a virtual file. Once we hit the path for the virtual path provider and the file, the web server is just going to serve it up as though it's a file on disk. Because it treats it as though it's a file on disk, any ASPX code that gets loaded for the first time is going to compile down to the temporary ASP.NET directory and leave some artifacts there for people doing DFIR to come collect. I'd like to say the reason I didn't use this tool was because of that offset consideration, but for life of me, I couldn't get this POC working against what my target application was, and causing a denial of service every time I tested it. My shell worked, but the rest of the app didn't work for everyone else, so not particularly stealthy. I've also included a link to Google Project Zero, because the person that developed the activity surrogate selector was James Forshaw, and he's got a deep dive if you really want to understand how that gadget works under the hood. So if we take this new knowledge and we apply that to Michelle's design, what I've done is I've taken my code from the ASPX and I've shifted it into another C# assembly that we're going to wrap up in a serialized object, and then we'll use that for execution rather than a file on disk. So if every request we make to the web server, as long as it's expecting a view state, we're going to be able to execute our arbitrary code. So what we do is we have our DLL, we load and save to a global key value pair, just as we did before, and then we retrieve the assembly on subsequent requests and hand through execution, and then the remainder of the server-side components haven't changed. But we no longer need a requirement to drop a file on disk. The other fun aspect of getting those machine keys is even if you get detected and they don't work out what's happening and don't rotate those machine.config files or the key within them, you pretty much got persistence, so you can just come and go at free will without having that file on disk, which is pretty awesome persistence technique. So we go into the demo. I'm going to delete the previous files. We need to regenerate them. I'm going to delete my web shell from disk. I'm going to quickly show you that there's nothing funky going on here. This just prints out hello world. And the only reason we need this page is we need something to target with our view state. So we hit hello world and hello world. So now what we need to do is update our config file, enable the view state and put in our validation key, which we'll see down the bottom there. So we want to hack my IS server, quick take a screenshot. So we've updated the config now. I'm just going to point out the hello world file on disk. And we can regenerate this time our bootstrap DLL, what I call the bootstrap DLL, and then the web shell assembly again. So you see that's been created in the demo directory. And now I can just use the tool exactly as we did before. So from the operator's perspective, nothing's changed. We're just changing the way we set the config. So we have a look at the outgoing request in Burp Suite. We have this massive base64 encoded blob, which is our assembly wrapped in a activity surrogate selector gadget. And we'll see we've got a successful load. So now we can go ahead and execute arbitrary C# assemblies exactly as we did before. Again, it looks like it's running in the PowerShell console, but it's actually running in the IS application. And there's the output there. So I didn't want the blue teamers to go empty-handed today. So I tried my hand at creating a Yara rule, and this manages to detect the client application. I tested it on my dev VM and my operator VM, 100% detection rate, so feel free to take a screenshot. Jokes aside, there is one nasty characteristic of this technique, and that's the fact that we're just loading unbacked .NET assemblies into the IS worker process. So probably not something every security team is going to be able to target, but probably something I'd expect EDR vendors to be taking a look at. So we look at the .NET assemblies in Process Hacker. We can see we got seatbelts sitting there in memory, very OPSEC safe, and then also my bootstrap assembly and the web shell assemblies. So that's what I would target if I was an EDR vendor. If you're an operator, you want to make sure you clear out that app domain once you're done. So you can flush that out, and then once it's flushed, it'll reset the app pool back to default, and you'll see that the C# assemblies are now gone, and there's nothing for my friends in DFIR to come pick up. Thank you. Any questions?
I am a super genius.